observed microwave background is isotropic, and the fact that, and the quote unquote the reasonable assumption that there is nothing special about the point where I exist in the universe, these two together imply that the universe is homogeneous. And then I had mentioned that since we do see galaxies, and these galaxies and other structures are supposed to have originated because of gravitational collapse of some initial density perturbations, we should see some imprint of the density perturbations on this CMBR. Because although at a more recent time here, I see developed structures like galaxies, one believes that they should have started from smaller perturbations like gravitational collapse, which means during the history of these, they would have at least existed as small perturbations when the matter and radiation decoupled in the universe. Which means that these imprints of small perturbations in matter, the small perturbations in matter should have left an imprint on the circle of last letter or the surface of last letter. Okay? And if that is the case, then there will be something like the number density of matter here may be different from number density of matter here. Now, in the case of what one calls adiabatic perturbations, which are supposed to have been generated by inflation, as the other speaker would tell, I hope. Okay? So, in that case, the matter density perturbation is proportional to the radiation density perturbation, which means that if there is more matter here than here, the radiation density here will be more than the radiation density here. Now I also know that the radiation density is proportional to the fourth power of temperature, because what one assumes is although the density is higher here than here, here also it's a black body radiation, here also it's a black body radiation. Which means since temperature is the only parameter which characterizes the black body radiation, one can say that the temperature of radiation here is more than the temperature of radiation here, which means that if I take my telescope or my whatever microwave dish and scan the sky, then the temperature of radiation here will be more than from in this direction, and this is basically the introduction of small amount of anisotropy. Now, the hunt for anisotropy itself is a very interesting story. The isotropic background in cosmology, the isotropic background of CMBR was seen in 1965, as I mentioned, Penzias and Wilson. One also had a reasonably developed theory of galaxy formation or structure formation. And as I said, theories of structure formation in general implied that there should be fluctuations, there should be anisotropy in the microwave background. However, as they kept on trying to detect anisotropy at a more and more minute level, they always failed to detect it. Till in 1990, they launched a particular satellite called the COBE satellite, Cosmic Background Explorer. Now the COBE satellite had 3 instruments on board. One was called one was FIRAS, which is Far Infrared Astrospectrophotometer. Then there was another one called Derby, and there was a third one which was to detect anisotropy, DMR, that is differential microwave radiometer. Now the role of these were the following. Derby, which is I think deep infrared explorer, background explorer. So that was used for calibration. Whereas the other 2 instruments, which was DMR, this was the one which was supposed to look for anisotropy. And the other one called FIRAS, which was supposed to look for deviations from the black body spectrum of the CMBR. Now, experiment was just before COBE. It was a very crucial experiment because had COBE also not detected anisotropy, then what would have been a big soup, because the allowed parameter within which one had to detect anisotropy so that all our theories of what we are doing over here is correct was very critically hinged on the fact that one better see some anisotropy in that. And it so happened that in 1992 they actually detected it. Okay? And so this DMR, just to tell you, the way it worked is, okay, so in the anisotropy measurements, operationally, what one does is, one looks at, so this is a radio dish, so looks at two different directions and gets a temperature difference. Okay? So you know the temperature difference in two directions. But you see, okay, so at this point, it is good to sort of recall what is the question we ask in cosmology. In cosmology, when you are talking about structure formation, one doesn't ask a question whether at a particular point the galaxy is there or not. For example, suppose you are doing geology, okay, some tectonic movements of the surface. You will not ask at a particular point whether mountain will come up or not. What you will ask is, in a given surface, how many mountains will come up within this height to this height. So it is a statistical information which you are seeking, and not an exact information of whether at a particular point a mountain will come up or not. Similarly, in the case of structure formation, the question you address is a statistical question. You ask a question, how many galaxies will form within a mass range m and m plus dm, and or how many galaxies will be there within this mass range in a given volume. You won't ask a question at a particular point whether there will be galaxy or not. So what you seek is statistical information. And so, making an observation in two different directions is not enough. What you need to do is, you need to have some statistical information. So what one does is, you have these two directions, and then, actually there are some very interesting things which they did in this. See, so, and you know, you are going to, this is on 2.73 Kelvin, and all indications which you are giving was that the temperature anisotropy will be less than 10 to the power minus 6 Kelvin, okay, and delta T, 10 to the power minus 5 Kelvin, less than that. So which means that in order to remove all the noise, they had to cool it down quite a lot. So they had an onboard liquid nitrogen cooler, okay, and then with this, when it is seeing in two particular directions, you have to average it. So what happened was, with one as the axis, this will be rotated, and the temperature at different directions will be measured, okay, and an averaging is done. In addition, this entire thing will be rotated in 2 pi degrees, okay. But while doing this, one has to be very careful about something, that in this rotation, it should not happen that it starts facing the sun, okay. So it is a very ingenious way in which they designed the whole thing. But you know, all this, you know, having said this, there is one remark, you know, there are two kinds of experiments. One is satellite based, the other is ground based. Now, ground based experiments, of course, the downside is that you have to go through the atmosphere, okay, so you have a lot of aberration. So you put satellite based experiment. But that satellite based experiment, the downside is the following. You see, satellite based experiments have to be planned from a very long time. Like for example, COBE satellite, it recorded the observation in NT2, it was launched in 90, but the complete blueprint of how the satellite is going to come up is in 1980 itself. Which means that the technology which goes in is actually old technology compared to other time. So this is the thing which you have to weigh pros and cons. Okay. Fine. So they did this thing and then got a map of the CMB sky, and they calculated the temperature difference in different directions statistically. I'll just come to what exactly it is. When they did this, they found that there is a root mean square fluctuation of about 10 to the power minus 6 Kelvin. Okay, actually it is 1.8 10 to the power minus 6 Kelvin. And so this was the first detection of anisotropy in a microwave band. Okay, and now, so I will go to the details of this, but to begin with, let me just tell you some basic aspects about how one analyzes this anisotropy. For this, let me again go back to this 1 plus 2 dimensional universe. Suppose we are living in a 1 plus 2 dimensional universe, and we were trying to find the anisotropy on the circle. Then what do? So I have the center here. So I have this one, and then I have first of all temperature as a function of theta. Okay, temperature in different directions. This is a two-dimensional picture. Now what I do is I integrate this over 0 to 2 pi and define what is called the average temperature. Okay. Then I define the deviation from the average temperature, which is a function of theta, as T of theta minus T naught. Okay. And you see, it is like this. Suppose I want to find out the, suppose I have a, I have a plateau, and I want to find out how flat is the plateau. It is not enough if I tell you what is the mean fluctuation of the height at different points. For example, suppose I have a plateau which goes up like this and has some fluctuations like this. This is one case. Suppose I have another plateau which goes up slightly and has fluctuations like this. Now the amount of fluctuations is the same in both, but clearly this is more flat than this. In the following sense, that what is important is not the fluctuation per se, but the fluctuation over and above the average value. So here, if I say the height h at a point x, and I measure the fluctuation in height at a point x, this may be the same as the fluctuation at the point x. But what I will be interested is delta x by h naught, the fractional fluctuation which is there. The important is the fractional deviation from the average height. So since my h naught is greater here and h naught is smaller here, this fractional thing is more. So this is what, so when I say small fluctuation or large fluctuation, because see, okay, this is one thing which I always mention, small or large does not make sense when you are talking about a dimensional number. You see, an ant is small compared to an elephant, it's large compared to a bacteria. But when you say small or large, without having a comparison to another scale, you can only make such a statement about a dimensionless number. It is much less than 1 or not. So in that sense, this is a dimensionless number, and this you can talk in terms of small or large. And it is this fluctuation which was observed to be very small, which is 10 to the minus 6. Okay? So now, so this is delta t, and because of this, what you are interested in is not delta t theta. What you are interested in is delta t theta by t naught, just like delta hx by h. It's a fractional perturbation on the average. And yeah, so this quantity is about 10 to the minus 6, because the 2 points are there. Now, this is one description that I can tell the temperature at every point. There is an alternative way in which I can do it. What I can do is, I can Fourier transform this one. Okay? Not Fourier, write a Fourier series, because a Fourier series is for a periodic function. Now this, since it is defined on a circle, this delta t by t naught is a periodic function. Okay? So, I can Fourier transform this, and one can have the Fourier variables ak. Okay? And so I can either describe the temperature fluctuation on the circle in terms of delta t by t naught as a function of theta, or in terms of its okay, I call it L because it's theta. Okay. dl delta t by t theta. Okay, so I can talk in terms of this. Now again, if I want to talk about the statistical properties of the fluctuation, what I will need to do is to use this, take the mod square and take an average. That is root mean square fluctuation. Okay. Now, in the case of 1 plus 3-dimensional thing, we do not have delta theta, t theta, but we have theta, t of theta and phi. Okay. So now, in the case of 1 plus 3 dimension, I have t of theta and phi, and I will integrate it over d omega, the solid angle, divided by the integral of the solid angle, and this I will call as T naught, which is the average value. Okay? And now the fluctuation in temperature at in any direction characterized by the two angles theta and phi will be given by delta T by T naught, theta and phi, theta and phi. And now what I did here, I had it as a function of theta and it was periodic in theta, and so I did a Fourier series. What is the corresponding thing I do on a spherical surface? I do it in terms of spherical harmonics. Okay. So I will expand this in terms of spherical harmonics. Okay. And this will give me some quantity just like AL there. Here there will be two variables because there are two angles, ALM. Okay? And this, okay, so now, okay, for a given value of L, there are several values of M because it's the same as the quantum mechanics L and M. M goes from minus L to plus L because it's the same Y and M, right? For any given value of L, YLM, M will go from minus L to plus L, integral jumps. Okay? So, so these many values of M will be there. So, in some sense, what you can do is when you want to average it, see, if you want to average here, I'll do a mod square and average over theta. If you want to do it in terms of this, one actually does this over different L. This averaging over different L from minus L to plus L. Okay? And this is what not equal to, but this is what is related to what you plot CL. When you do this, when you must have seen this graph for microwave background anisotropy, you always plot L plus 1 CL versus L, and then you have this. It is this CL which you actually calculate. Okay? So, what is calculated is, once again, the fluctuation in the delta T by T, the Fourier transform of that, the mean square value of this. And I mean, you know, when you want to calculate the power which is there here, then it is not just CL, but L into L plus 1 into CL. Just like when you do Fourier transform, you know, if suppose you have a signal f of t in one dimension, and you have f tilde of omega as a Fourier transform, then the power which is there in this signal is omega to the power half times f tilde omega. Okay, so so the similar calculation will show that what the amount of power in the microwave background anisotropy is L into L plus 1 times CL. So this is what one does for broadly one does for analyzing the anisotropy. Okay, I will come to details of how you calculate delta T by T and what are the factors which affect it and so on. Okay. So the next thing which we have, characteristics which we have of the of radiation is polarization. Okay. Yeah.
So what is the reason we average over N?
So this is about anisotropy. So the next characteristic of radiation is polarization. Now you may ask that, you know, the universe was having charged particles everywhere before recombination, radiation was coming, and it was all random. So where is the polarization coming from? Okay, and for this I will give you an interesting example, which I don't know whether you have noticed it. Have you ever looked at the sky with a polarizer? Just the plain sky with polarization. At sunrise or sunset? Okay, so let us look at that. So Here is the observer looking at the sky, and suppose you have the time of sunrise is here, and consider a photon from the sun which is coming in this direction. Now I am looking at it in this direction. Suppose you have an electron, a free electron in the ionosphere. Okay? Then what happens? Since the radiation is coming in this direction, this radiation has oscillations in electric field in two directions. One is in this direction, the other is in and out of the moon. There is no oscillation along the direction of propagation. Now this radiation comes and jiggles this electron. So what happens? The electron reacts again by oscillating like this or in and out of the moon. Remember that there is no oscillation in this direction because there is no electric field oscillation in this direction. Now, because of this acceleration, the electron will radiate. Okay? Accelerated charged particles radiate. However, the oscillation in this direction will not contribute to radiation because this gravitational energy. The only component which gives radiation is the one which is oscillating in this direction, and hence the light which you are getting here is polarized. Just do this experiment. You take a polarizer and look at the sky at sunrise and then rotate it. You will find the change of polarization. What will happen is there is a lot of background light, so it won't be dark and bright, but there will be an undulation of darkness and brightness, either at sunset or at sunrise. Now clearly this will not be there at noon, because when the sun is here, the oscillations are this, and this is precisely will give me both the things. Okay, so it's unpolarized. Okay, and I mean clearly, just because you jump from here to here, there should not be a discontinuous change. So when you actually go from another direction, so the polarization gradually changes till it becomes 0 degree of polarization when you actually face the sun. Okay, so the summary of what I said was the following: that here I have charged particle, I have Thomson scattering from charged particle, I have radiation which has an anisotropy. It is coming from this direction and not that direction. So if I have anisotropic radiation which is incident, I have charged particles, and I have Thomson scattering from charged particles, in general I will pick up a non-zero value of polarization. Okay. So where does all this fit in the case of cosmology? Now I talked about the epoch when the matter and radiation decoupled. Okay, so this was the epoch. Now look at here a simple picture that suppose this was one point from where I was receiving light. Here there is an electron from where the photon got scattered for the last time. Here, let it be the time when the photon got scattered by last but one time, the previous. Now, because of the existence of anisotropy in the microwave background, the radiation which is coming from here to here has a built-in anisotropy. I was just telling about delta T by T. So, this case of sunrise, light from sunrise, is just a extreme case of anisotropy. However, because of the delta T by T as a function of theta and phi, there is some anisotropy built in. That is, the light which is reaching the last scattered electron from the last but one scattered electron, that light has a certain degree of anisotropy. So, this electron sees some anisotropy because this is seeing some from this direction, some from this direction. So just like here I was looking at that circle of last scatter, look at this electron. The electron will also have its circle of last scatter. And there is anisotropy from there. So you have all the three ingredients. You have anisotropic radiation incident on the charged particle. You have charged particle, and you have Thomson scattering from that. It picks up a certain degree of polarization. Okay? So this is one case where it picks up polarization. And another case where it picks up polarization, which happens to be much more important, is related to what Thiers was telling you. Thiers had told you about reionization. Reionization, electron, proton, separated, ionized. Okay. So he must have talked about at a later stage when matter which was neutral reionized because of radiation. He must have talked about, star formation and energy coming out of it. Hey, what has happened? A team had given a talk.
Talk about reionization only, talk about structure formation.
But he was supposed to talk about reionization, right? Structure formation. Nobody has done reionization. Oh, I see. That it becomes neutral and they lived happily ever after in a neutral. It never happens again. Okay, life is not always happy. Okay. What happens is there are various processes which can happen here. Some of them being, some of the prominent things being star formation. Okay. Now you can have a situation, for example, something called Porphyry stars, which are very early stars, supposed to have been formed, very massive stars. And so when they collapse, there is a lot of energy which is input, because of gravitational collapse, and this energy gets into the universe. Now this energy, something has to be done. It's like, Samudra Manthan, Vish, Amrit, both come, something has to be done with it. Okay? So this energy has to be, something has to be done with energy. This energy is absorbed by the matter and they reionized. So this whole thing about the universe being neutral here is a kind of an absolute zero order picture. It doesn't happen in reality. Now we have observational evidence that it is not so. Okay, so let me just tell you, why do we say, on what basis we say it is not so? See, for example, suppose I have light coming through neutral medium. So suppose I have hydrogen and I have light coming in whose frequency almost matches the ionization energy of hydrogen. You will expect that some of the atoms will be either excited or ionized, which means that will be observed. So which means that if suppose I have light of different wavelengths coming from background and I do a spectral analysis of the light here, I will find that there is a dip corresponding to those lights in which there is an ionization taking place, because they have been observed. Okay? It means that although all this is fine, that I am looking at microwave background, it is coolly coming to me and literally coolly 2.6 something coolly coming to me, and all that is fine. But the point is, if there is neutral matter here, there will be some of it which will be observed. And you should see the absorption spectrum. You don't. Which means that the matter in the vicinity, you don't to the extent to which you expect. Okay? It means that the matter in the vicinity, a part of the matter at least, is already in ionized form. See, only if it is neutral, it can eat up some more photons and ionize. Here it is already in the ionized form. Okay? So then there are a lot of things like, did he mention Lyman alpha cloud? These did not mention Lyman alpha cloud, that one. Okay, this is bread and butter. Okay. so there are something called Lyman alpha forest and so on. Okay, so which you see, which gives indication that the universe is ionized. Okay, so I've done more than just mentioning. So let me just continue with my statement. Okay, so then so suppose in this region you have ionized matter. Once again, because of the anisotropic radiation coming from the surface of the scatter, delta T by T as a function of theta and phi, and ionized matter here, you have some more signals of polarization. So reionization of the universe can also lead to polarization. Okay. The third thing, before I just wind up over the rough details, the third thing which is important is to do with the spectrum. Okay. So what about the spectrum? See, when you have a Bose-Einstein distribution, in general, you will have a non-zero chemical potential, mu. Now, in the case of photons, the chemical potential is zero. Now, what is the physical origin of the chemical potential? The physical origin of or physical or mathematical, you will call it whatever. See, when you do, say, equations of motion in classical mechanics, you start with a Lagrangian, you start with an action, you have a Lagrangian, you vary the Lagrangian, get the equations of motion, Lagrangian equation. However, suppose you have a constrained system, then you need to introduce Lagrange multipliers to take care of the constraints. Okay. So the fact that you have constraints leads to a non-zero value of the Lagrange multiplier. In the case of the distribution of, say, particles in general, bosons, then when you have a number conservation, okay, so you have an interaction which is going on between bosons and some particles, and you have a distribution function, and in order to get the equilibrium distribution function, you need to minimize the equilibrium, just like Lagrangian case. You know, you vary it and find the minimum for the, so that the change is minimum, it sort of settles down to the equilibrium. Now in this process, one thing which you need to put in is the fact that the number of particles is conserved. Okay, if AB going to BC, the number of particles are conserved. Hence, if you want to extremize the distribution function and get the equilibrium distribution function, you need to incorporate the fact that number conservation is there. This you do it by introducing a Lagrange multiplier. The Lagrange multiplier corresponding to the number conservation is nothing else but chemical potential. So if you have a number conservation, conserving system process, then the chemical potential will be non-zero. In the case of photons, you do not have this constraint. Photons can be created or destroyed. And hence, this chemical potential, the Lagrange multiplier is zero, the chemical potential is zero. That is why the black body distribution is a Bose-Einstein distribution, but with a zero chemical potential. Okay, so this is the origin of why in general zero chemical potential. However, you can have certain processes in which this is not true. For example, suppose I have the familiar picture, Compton scattering. What happens in Compton scattering is you have one photon in, one photon out. So Compton scattering is a process in which number of photons is conserved. And because of this, when a process is dominated by Compton scattering, it introduces a non-zero chemical potential for photons. Okay? Now, so basically what happens is, if suppose you have the black body distribution, so this is mu, this is rho or I or whatever, okay? This is the black body distribution. And if, so when you say a Bose-Einstein distribution, that is also an equilibrium distribution. So it means that if suppose I have a bunch of photons and electrons and allow them to interact purely by Compton scattering and wait till it reaches an equilibrium, then it will reach a Bose-Einstein distribution with non-zero chemical potential. Okay? So there is clearly a difference between Planck spectrum and this. So there is, first of all, you see that there is a good case, I mean what they call in legal language a prima facie case for a distortion of the Planck spectrum. Okay? So now, but you know, most of the time what happens in cosmology is that you don't have enough time for it to equilibrate and form a Bose-Einstein distribution, but there is a tendency, there is a few steps towards the deviation. So let us look at it at a microscopic level, how the deviation happens. Suppose let us look at one particular thing. Suppose I have an electron which is at a high temperature. Okay? And you, so I don't know if it's in Compton or inverse, probably this is inverse Compton what I'm saying. Yeah. I mean low energy electrons interacting with low energy photons interacting with high energy electrons. Okay? So what happens is, say at this frequency the photons which were here, they have got promoted to a higher frequency. Okay? And it happens throughout. So what happens? This gets distorted to this. You may wonder why it is intersected. See, remember that two Planck distributions never intersect. Okay? So if I have a Planck distribution of this and another temperature, it will be like this. It will be you know, like one curve inside the other curve. But remember that this is no more a Planck distribution. That's why it can intersect. Okay? And so there is this point of intersection. Okay? Another way of plotting this is, instead of plotting I plot I minus I Planck. That is, I just plot this deviation. So what happens is, with respect to nu, till some point it is below what will be in Planck. So it will be something like this. At some point, this and this will be equal. The Planck distribution and the real distribution. So this thing will be 0. And after that, it will be nu. So if I plot the deviation of the Planck distribution, then you have this process. This is the kind of, this is the nature of the curve which I made. This as such is not surprising. But what is beautiful is the following. It turns out that this particular intersection, okay, can be calculated exactly. That is because if you go through the details of the calculation, the point where this intersection happens, okay, suppose you have electrons and photons which are interacting, this frequency where it crosses the Planck spectrum is governed by fundamental constants. Mass of electron, Planck constant, speed of light, and so on. So you know exactly from fundamental physics what is its value, and this happens to be about 220 gigahertz. And this is called, and this particular effect is called the Sunyaev-Zeldovich effect. Like many things in cosmology, Sunyaev and Zeldovich have done this. Okay? And yeah, so now, where can you observe this? There are two situations where you can observe it. One is what I was telling you, that suppose the universe is reionized. Then you have radiation coming through reionized matter. So you have free electrons, you can undergo Compton scattering, and you can get the signal. However, all attempts to see the deviation are failed.
Excuse me, sir.
Yeah.
Sir, is there any significance that this particular frequency is showing a matching with the black body distribution, like the value for the black body distribution? We are comparing two curves. We are taking a black body ideal theoretical curve and one which we are observing, distribution we are observing.
No. Here none of them is observed. What I am saying is there is a black body curve, because this has not been observed in cosmological context. Okay, I'll just tell you. This is a black body curve. If you have an enhancement of the energy of photons by Compton scattering, this will be the curve. Okay, so forget about observing. Take any such curve and see the intersection. This will be governed by these parameters like mass of the electron and so on. See, it is because the basic process involved in Compton scattering. That's all.
So the way the photons are reaching equilibrium through Compton scattering and the way they do in ordinary black body theory, it is the same.
Yeah, because in the you see, usually you do not have a number conservation of photons. If it is Compton scattering dominated, number conservation of photons is there.
So that is different.
So it's different, yeah. Yeah, that's right. The equilibrating process is different.
Sir,
Yeah.
this is the only process where mu is not 0 quantum scattering.
Yeah. For photon.
Photon. So, sir, in case of other boson particle, if you are talking about chemical potential.
Suppose you have boson, yeah? Suppose you take, say an atom. Helium is a boson. Helium atom, helium. Only for black body it will be 0. So for this, yeah, that's correct. Yeah. Neutrinos are fermions, although they are massless, so that doesn't happen there. Okay. So yeah. So all, I mean, so this instrument called FIRAS, which I was mentioning in COBE, that is the one which was looking for this deviation from black body spectrum. Now here I should mention some interesting thing about how they measured that. Why it's called infrared? It's called far infrared astrospectrophotometer. Why is infrared? Because to measure this, they do something interesting. What they do is, they just look at this region, in this band, a low frequency band, which is the Reionization region. Now, if you look at this, what will happen is, if you look at this curve, there will be another curve like this, which will be a black body curve. but it will be very close to this, this deviation curve at low frequency. So what they actually look for is, especially in the low frequency region, they look for what is the change in temperature. Because although the curve is this, it will disguise itself as this curve for black body in this region. So when they look for a low frequency, it will appear as if there is a region where there is a dip in temperature. Okay? And this delta T which they measure is to do with the spectral distortion. Okay? And since this is the Rayleigh Jeans region, low frequency region, that is why far infrared astrospectrophotometer. It's the infrared region where they focus to get this information. Okay? And COBE and all experiments have actually put a bound of less than 10 to the power minus 5. What I mean is the following. If T naught, which is 2.73 Kelvin, is the background temperature, and this dip in temperature, this apparent dip in temperature, because this you cannot say temperature because it's not a black body spectrum, but it corresponds to this one at low frequency. So it is corresponds to this temperature. This change in temperature, that delta T by T naught is less than or equal to 10 to the power minus 5. Remember that this is not the anisotropy case. This is even in the homogeneous case, there is a dip in temperature in that region. Okay, if you just measure this. Okay, so this has been seen to be less than 10 to the power minus 5. So the question is, does this such an effect exist at all? Or is there something wrong in what we are doing? It turns out that it does exist in a slightly different context, although in the context of CMB. And so it gives us a feeling that it is only a matter of time and technology to get the actual value. And the context in which this appears is the following. Suppose this is my surface of last cat from a CMB instrument. And suppose the observer is here. Okay, or if you're a radio astronomer, then you can put a radio dish. Okay? So, and you're observing it. And suppose you have a cluster of galaxies. Now, one thing with cluster of galaxies is, inside a cluster of galaxies, because of some various processes, there are a lot of hot electrons, free electrons. Okay? So it's like the cluster of galaxies are inside a cloud, the cloud consisting of a lot of free electrons, high temperature free electrons. So here, there are a lot of free electrons. So now what will I do with this telescope? I will scan the surface of dark scatter in different directions. When I am looking in this direction, I will see 2.73 Kelvin. Okay. Suppose I am seeing only in the low frequency region, the infrared region. So as I move the telescope, I see 2.73 Kelvin. But when the telescope is looking at the CMB through the cluster, the CMB photon which comes here gets Compton scattered by this electron and hence gives an apparent decrease in temperature. So what happens is, if you plot the temperature by just measuring the Rayleigh Jeans region as a function of theta, then you will have something in the small region where the cluster there will be a sudden dip in temperature. So here, by looking at CMB through the cluster of galaxies, you can actually ascertain that there is actually free electrons sitting there and a Compton scattering thing is occurring. So this actually, by this we know that what we are talking about is actually a realistic effect. The question is, so here it is happening when there is a specific region of high electrons and photons are coming in and this absorption is going on and scattering is going on. But of course the bigger question is, suppose you have reionization in which there is a homogeneous distribution of free electrons. Do we see an isotropic decrease in temperature? That is yet to be observed. Okay? So these are the three things which are there in radiation. Now what I will do is, be ready, otherwise we will break and start now. After that. No, because now I will start with the next hour, I will start with some details of the calculation of anisotropy and polarization. So I think we can break for that and then come back, because then there will be a break in between otherwise. advertisement which said, one is telling the other, no, you are too old for something, you are too young for something, but you are just right for Amul milk chocolate. Okay? So this 3 1.5 hour slots, it is too much for an overview on CME physics and too little for a detailed thing. So, okay. Okay, so let us now look at anisotropy, and my whole idea will be the following. I will just capture some details of this anisotropy and to how the physics of other things are related and how it manifests itself in anisotropy in a more quantitative way. Okay. So what we do is, when you want to study the distribution of photons. So basically, when you say anisotropy, I want to see the distribution of photons in space. Okay. So if I want to study the distribution of photons, what I need, the best way to start at the 0th level is to start with the distribution function f. Okay. So let me denote the distribution function f, the distribution function of photons, that is the number of photons at time t xi within a momentum region p pi. So this is magnitude and this is direction. Okay. Now, so what I need to do is, if a system is not in equilibrium, then this by interactions, this distribution function will evolve in time. So you need to calculate df by dt. Okay. The thing which makes this df by dt non-zero are scattering events with other particles. Okay. Among each other or other particles or also the container. Now, so before that, let me just mention a few things about this. That if suppose there is no collision, okay, then df by dt is 0. The situation is something like this. Suppose I take the case of an incompressible fluid. Okay. Then what happens? Suppose, so let us take 2 cases. One is, I have some oil dropped in water, and the other case is, I have some ink dropped in water. Now, what happens to the oil dropped in water? In the oil dropped in water, the density of oil per se does not change. So what happens is, in the process of mixing, this blob of oil which has come will get distorted in various things, the shape will change. But since the density is same, the total volume or the area occupied by that blob remains same. Okay? So that whole patch will get distorted in various ways, but the density will remain same. Which is different from the case of ink. Okay, of course at a very microscopic level the same thing happens, but at a reasonable macroscopic level, the ink particles itself, they themselves disperse in the fluid. So there what happens, the density of ink pigments itself changes with time. So the case of oil distorting itself is like a collision in this case. At a microscopic level, the oil does not intermingle with water. It maintains its identity and just keeps getting distorted. So the df by dt or d rho by dt there is constant, is 0. Rho is a constant. Okay. Whereas in the case of ink, because of its individual interaction with water molecules, it gets dispersed. So what happens? The density of ink pigments keeps reducing. So d rho by dt for the ink pigment is non-zero. So in other words, from this simple analogy, you can say that collisions are something which tend to change the distribution. Okay. Now, this was the case of real space. In the case of phase space, something similar happens to distribution function. When you have a set of particles which do not undergo any collision, then, so in a phase space, suppose I just have a one space dimension. So the 1x and 1p. So I have some region where the particles are there. By its evolution, it may evolve later into some kind of a shape, but the total volume will remain same. Okay, if there is no individual collision between particles. So suppose, consider the case of photons, in which to begin with, let me forget about collisions. So now, here, df by dt will be 0. However, in the calculation of df by dt, as I was just saying, the exact expression of df by dt will depend on my background geometry. And my background geometry is governed by gravity. You see, because in GTR, gravity is not a force. It just distorts geometry so that all your equations of motion take a different form. So similarly, df by dt in the presence of gravity, the exact expression will be different from df by dt in flat spacetime. As a result, although there are no collisions, because of the curvature of spacetime, okay, there will be an evolution of f. Okay, that is what I will come to. So before this, let us. So as I said, f will evolve because of two reasons. One is collision. The other is gravity. When I say gravity, I mean in general, no, time-dependent space-time. Okay, time and space-dependent space. Okay, and yeah. So let us take a very simple case first. Let us take the case of a homogeneous isotropic difference. Okay, and let us see, before we go into perturbations, let us see by this method are we able to reproduce the result which we did yesterday, okay, in this more detailed way using distribution function. So now, if suppose you have a homogeneous and isotropic medium, old age forgive me, okay. Okay, if you have a homogeneous and isotropic medium, then yeah, then the form of f will not depend on space points. It will only depend on the energy. Okay? And since they are photons, energy equal to momentum, c equal to 1. Okay, because yeah, so P is E by C. So it means f will be a function of P, and let us parameterize it by some quantity t. So it is, so f is a function of P and T. Okay. In particular, when you have the pan distribution, it is e to the power P by T minus 1. I mean, P by T means P into C, or E by C, and then K equal to 1. Okay. But this exact form is not needed for us. We will just say that at a homogeneous isotropic level, this is what it will be, and this is homogeneous isotropic, I will call it C. Okay. So there is no perturbation. Okay. So now let us look at this thing, df by dt. Now this df by dt will be equal to del f by del t plus dp by dt into del f by del t plus the direction cosine of P plus dxi by dt del f by del xi. Okay, so this is just with respect to time, with respect to space, and with respect to the components of momentum. So I don't know px, py, pz. I have written it in this way. Okay, and now if suppose there are no collisions, okay, this quantity will be equal to 0. Now if I am assuming that the form of f is this, then clearly this thing drops out. There is no space dependence on the distribution function. That is, the distribution function of photons is same at every point. the distribution function of photons is independent of direction, because in black body spectrum, the nature of radiation from any direction is the same. So, because it's just a derivative with respect to direction, so this will also be 0. This is the variation with respect to directions. This will also be 0. That leaves us only these two terms. So, for the case of F0, I have del F0 by del T plus dP by dt del F0 by del T equal to 0. So, this is the equation which I need to solve. Okay. For the case of distribution function of anything which is a function of just P by T. Yeah.
Why there is not d theta pi by dt?
P theta?
Theta pi there is in right hand side third function.
No, I have just split up that the momentum space derivative as magnitude and direction. That's all. See, instead of doing dx, d by dx, d by dy, d by d theta, I can put it in terms of d by dr and d by d direction. So here there are two things. There are more things hiding here because of summation override.
So these are unit vectors or things?
These are unit vectors. That's why it's a directions. See, I have split this momentum as a magnitude and the direction. Oh.
Theta pi by dt should be there.
This is what you mean.
Yeah.
You're right. Yeah, you're right. Yeah. That's right. Thanks. Okay. So because df by dp is 0, this goes in. Okay. So this is equal to 0. So now let me try to play around with this. I have this momentum. Now momentum is an independent variable. It's not a function of time, because I am not, you see, okay, this is one thing. See, often when you do Lagrangian dynamics, you have L as a function of x, x dot. You treat x dot and x as independent. So why do you treat it independent? Because velocity will change in position, right? Why do you treat it independent? So you get my point now. So when you have a particle which is moving, suppose you have projectile motion, then at different points it has velocity is different. Okay. When you are writing the Lagrangian, you are using velocity and position as independent. Why?
Because they treat it as separate genres, they are separate genres coordinates.
Why? I mean, but you know that velocity is changing. You see, you need to distinguish between coordinates and trajectory. Trajectory, see, for example, suppose you have a large desert and on which a truck has gone. Okay? Now, in the desert, every point of x can have any value of y. Then only you are having the full area. So every point of x will have every point of y. But what is it which singles out the trajectory? A given function of x and y. So in the case of Lagrange, when you do the Lagrangian equation, at the level of Lagrangian they are independent. What is, see, so when x takes the value of certain z of t and let the z of t become the function of z. But x dot and x are, as you said, independent variables. Okay? So what Lagrangian equation does is to relate these two. So before you relate these two, these are independent variables. Okay? Similarly here, the momentum here, this is not a momentum of a particular photon. This momentum is all possible momentum which a photon can take. So this doesn't have any time dependence. So there is nothing like a p dot here. Okay? So now, so if I, whereas this one is as the photon propagates, how the momentum changes with time. This is along the trajectory of the photon. So that is the difference. Okay? So now, here if I substitute for this f naught as a function of t, so let me do the following. So I will, yeah. So this will be equal to del p by t by del t. I will put it as f naught p by t prime. That is with respect to the argument, okay, which is this one. This plus dp by dt this is T, dp by dt, and this quantity will be, this is keeping time, temperature as a constant, so I will divide it by T and I will multiply by capital T. Okay. So this will be this plus 1 by T f naught prime equal to 0. Okay. Now this dp by dt, what you can do is, you can, okay, so now suppose I consider Gij as minus dt square plus a square dx square, I mean the unperturbed background. Then I can go to this Gij, calculate Christoffel symbols, calculate the geodesic equation, and find out what is the value of dp by dt. Right? Basically, what I need to do is to find out what is dp by dt. So in terms of gamma, alpha, beta, delta, I can find out, I mean you understand, no? The covariant derivative of, and so if I do that, the relationship which I will get is the following. dp by, yeah. So let me just rub this off. So I have del f naught by del t equal to del f naught by del p by t dp by t by dt. Let me just write it in this form. Sorry, just a minute, I am just goofing up a bit. This is equal to this one. Yeah, okay, so just a minute. So I have df nu by dt plus I have d by dt, df naught by dt, and then from here I write df naught by dt plus, okay, d, change from variable, okay, something wrong there. Okay, so I have df by dt, then I will write dp by dt as okay, so let me do the following. Let me leave this just a minute, I'm looking up. So if I have this one, so I have del p by t by del t f naught prime plus so this will be dp by dt, and this will be f naught prime into 1 by t equal to 0. Okay, and then what? So I then put the equation for dp by dt, and it turns out that if you solve the equation, be dp by dt equal to minus p a dot by a. If you put in all the values of gamma and no, because the derivatives of gamma, you will get derivative, because of gamma the derivative of Gij will come, and the derivative of Gij a dot will come. Okay, so this is what you get, and suppose if I substitute it here, I will have t f naught prime minus P A dot by A F naught prime into 1 by T equal to 0, and then I will have this, I will combine it with this one. Okay. Okay, and suppose, okay, and this I will write as, okay, this I will write as, since this P is independent of time, I will write it as P times del 1 by del T by del T into F naught prime. I will not happily P by T, I will write as H times F naught prime equal to 0, and this will be 1 by T dot, okay, so P is okay, fine, fine. Okay, so now I have got this thing in which I said that F naught is a function of P by T. Okay? So I will substitute it, and as I said, this I can write it as del P by T by del T into F naught prime. This is del F naught by del P by T. Okay? So this is this portion. This plus, I will substitute for this from the geodesic equation. This will be nothing else but minus P into H. This quantity will be minus P into A dot by A. That comes from the calculation of dP by dt from these gammas. This multiplied by 1 by T times F naught prime equal to 0. Okay? Is this clear now? Sorry for the confusion. Okay, is this clear? Huh?
That would be ds square. Gij.
Sorry. Correct, yeah. So Gij will just be the matrix. Okay. So this is there. And now I will convert this as P into 1 by T dot with respect to time minus P A dot by A. Now again divide by T, and the whole thing into F naught prime equal to 0. Okay? And now I will solve this further. I will write it as P by T square T dot with a minus sign. Okay? Minus P by T A dot by A equal to 0. Is that okay? Now what I will do is, I will take P by T outside. So I will remove this P, T, and then P by T, I will put it outside. Okay? So that means that this quantity is 0. It means that T dot by T plus A dot by A equal to 0, which means temperature is proportional to 1 by T. Exactly the same relationship which we got yesterday. Sorry for this confusion. Is this okay? I mean, or should I repeat? Huh? Not okay, good, okay. You understand till here? Because I have said F is independent of direction and F is independent of position. Okay? So this is there. Now all what I am saying is, because it is independent of direction, independent of position, F can only be a function of momentum. Okay? And another parameter called T, capital T. Okay? And so it has to be a function of momentum and that's a function of time. I am parameterizing by saying it's a function of momentum and some parameter 1 by T, okay, which is a function of time. Okay? And from the form of the Planck distribution, I know that the capital T is temperature. Okay? So I am characterizing this by, it's a function of momentum and temperature. So I can write this in this way. Since it's a function of only momentum and temperature, is this okay? No. if y is a function of alpha, then dy by d alpha equal to d, rather dy by dt is dy by d alpha by dt. So here alpha is p by t. Okay? Okay, so I can write it this way. And here dp by dt from calculation of geodesic equation, it will come out to minus p into h for a homogeneous isotropic universe. Okay? And here, this is a derivative with respect to p, partial derivative. So it's not, it's for constant time. Okay? Since capital T, temperature, is a function only of time, I can always put divided by time here. So I can divide by p by t and multiply by t here. Okay, so it's 1 by t and f naught prime equal to 0. Is it okay now? So now what I do is, I simplify this one. Here p is independent of t, so it comes out. So I have 1 by capital T dot. Okay? And here minus p is 1, I have taken f naught prime outside. So I have this thing, so 1 is 1 by t dot, it is 1 by t square. T dot by t square with the minus sign. Okay? So here it was p by t square minus t dot, into minus t dot.
Sir, since we are doing one derivative with respect to time, other with p, sir, don't we use different, f naught dash is different in both cases?
No. See, f naught dash is derivative with respect to its argument, which is p by t. That is why I have taken p by t outside here. See, it is the full argument, so there is only one variable. Okay? So I have this thing. So now this becomes, so I will just write this last step again. So here I have t minus t dot by t square minus p by t a dot by a into f naught prime equal to 0. Okay. So I take now p by t out, minus p by t out. So we have a minus p by t dot by t plus a dot by a f naught prime equal to 0. Okay. So in general, this will be equal to 0. So if t dot by t equal to plus a dot by a equal to 0, then t has to be proportional to 1 by a. Which is precisely the expression which we got yesterday from our argument about Planck distribution and then expansion of the universe and then equating rho going as 1 by a power 4 and rho going as t power 4. We equated and got t as equal to 1 by a. This is exactly what we have got from this more zeroth level argument. Okay. So what I am saying is, so this sort of assures you that this is not, it assures you that I am not cheating you, okay, by using Boltzmann equation. Okay. So now what we do is the following. This was for the zeroth level. Now let us see that we consider now the situation where the collisions are still 0. So the right hand side of Boltzmann equation is still 0. But my space-time is no more a homogeneous isotropic space. Okay. So when can this happen? What is collision? Here, collision is an interaction, collision with photons with anything is a non-gravitational interaction between photons and something. By which I mean this. Suppose I have a dark matter particle, then also the photon will interact. But this photon will interact gravitationally with the dark matter particle. Because of the gravity of the dark matter mass, the photon will do like lensing, it will do a deviation. However, if I have an electron, the interaction with photon and electron will be non-gravitational. Gravitation will be there, but that will be negligible compared to electromagnetic interaction. It is this non-gravitational interaction which I call collision. So in other words, if I, for the time being, neglect all electromagnetic interaction, then my collision term in the Boltzmann equation will be 0. Why? Because in a Newtonian picture, I would have considered the gravitational thing also as collision. However, in the Einstein's picture, what I do is, I say that gravity is not a force. Gravity modifies geometry. So, the photon continues to move in a geodesic, although in a geodesic in a non-trivial spacetime. So, in other words, the df by dt remains 0 even in Okay, if there are no electromagnetic interactions, there are no collisions. Only difference is when you have a perturbation in background space-time geometry, then the expression for df by dt has to be modified according to what it will be in a curved geometric space-time rather than a homogeneous isotropic geometric space. Okay, so df by dt will remain 0 when you have no collisions, but if you have background gravitational perturbations, then although df by dt will remain 0, the form of df by dt will be different now. It has to be modified as per the curved geometry. Okay, rather perturbed geometry, this is also curved. So as per the perturbed geometry, so the df by dt has to be calculated for a different metric and not the FRWT metric. That is the only difference. Okay, so we first take the case now that we have graduated from a homogeneous isotropic universe to a level in which the universe has, the photons have no collisions, but the universe is no more homogeneous isotropic. However, I will say that the deviations from homogeneity and isotropy is small. Okay? That is why I call it perturbation. So let me next characterize the geometry of space-time. By ds square equal to ds square equal to 1 minus, so what was it originally? It was minus 1 into dt square plus 1 dr square, or rather I will just put it as this times a square delta ij dxi dxt. So this was of this form in the unperturbed thing. In the perturbed thing, what I say is there are two functions which add up to this. Sorry, the convention here is actually this is the problem which one has if one follows different books, because different books follow different notations. You know. Okay. So now I start with this kind, this perturb. So basically psi and phi, these have dimensions of energy per unit mass. Okay. So they are like potentials. Okay. So this is the nearest Newtonian analogy is they are something like gravitational potentials. Although in Newtonian thing you have a single gravitational potential. In GTR it is the perturbation is characterized by two potentials. And in some special case when anisotropic stresses are 0, then psi will be equal to minus phi. In fact, you can look at it this way, that if suppose psi is minus phi, then you take the Schwarzschild metric. There if you call Gm by R as the potential and do a binomial expansion of 1 minus 2 Gm by R, you will essentially get this. Okay. Okay. So this is the perturbed metric which I am taking, perturbed line element, and now I calculate df by dt in this line element. So when I say I calculate df by dt in this line element, all what I mean is when I calculate dp by dt, okay, and all those derivatives and so on, I use the general relativistic expression in sense of geodesic equation and not just Newtonian. So if I do that, the answer which I land up is the following. This will be equal to minus p by a, where a is that scale factor, del f naught. The other thing is I write my f as f naught plus f1, which is a perturbation, and consider only linear perturbations in f1. That is why I call it a perturbation. The perturbations are small enough that I will neglect all quadratic quantities in the perturbation. If I do that, then I will get the df by dt up to first order. Okay? So I take the full df by dt, write this, then I write the df by dt for then I write the df by dt for the zeroth order thing, and then what we did earlier, and subtract this from the zeroth order. Okay, and so I get an equation for the evolution of the first order deviation of the distribution function. Okay, so df by dt to first order will be this thing by t, and okay, I'm actually disorganized in this. I should have mentioned something more. Sorry for this. Okay, so I have to say a few more things about this characterization of the perturbation. So, in general, without any loss of generality, I can characterize my f as 1 by e to the power p by t 1 plus theta minus 1. So, what I mean is the following. When theta is 0, this is just f naught. This is the usual Planck distribution. Here, what theta tells me is the fractional fluctuation in t. So, for example, if I have the distribution function as f equal to 1 by e to the power p by t plus delta t for a different temperature minus 1, I will write this as 1 by e to the power p by t 1 plus delta t by t minus 1. Okay? And this delta t by t is something which will depend on direction. A temperature in what I told on that circle of last scatter, the temperature in different directions. Okay, so this delta t by t is the same delta t by t which I referred to in the anisotropy. Okay, and this is where it comes and sits in changing the distribution function. And it is this delta t by t which is the fractional change, the fractional fluctuation in temperature which I call capital theta. Okay, so one can actually then binomially expand it for smallest values of theta, Taylor expand it, and then write it in terms of f naught some perturbation. Okay, so if I do all that calculation, I can finally write this whole thing in terms of this fluctuation. Is this clear? See, I am not calculating it, but I am trying to tell you the broad contours of how one does it. So, one already has the equation for f naught. Okay, the equation for f I have here, and since I am characterizing f in this way, I can characterize it in terms of derivatives of theta with respect to this and so on. So if I put all that into this and subtract it from the zeroth order thing, I can write the equation for the perturbation, and the equation for the perturbation happens to be this thing into d theta. Okay, before this let me write it in this form. D theta by dt this is what it is. Okay, so this is the equation telling you how the first order perturbation of f evolves. So here, as you expect, what are the perturbed quantities here? The perturbed quantities are theta is a perturbed quantity in the temperature, and psi and phi are the perturbed quantities in the potential. So as you expect, the final expression for the evolution of the perturbation in f has to depend on all these parameters. So that is what you see here, and if you put in all the geodesic equation, everything, you will finally get it of this form. That is, it depends on the time derivative of the fluctuation, it depends on the gradient of the fluctuation, it depends on the time derivative of this potential and the space derivative of this potential. Okay? So let us just try to analyze this. You see that gravity will come in through the components of G value. So the effect of gravity on my temperature dependence will come through this thing. Okay, because this is what has phi inside. Whereas this quantity is called the term corresponding to free streaming. What it means is the following. You see, have a distribution in which I start with a non-Planckian distribution. That is, sorry, not non-Planckian, which is not completely isotropic. That is, theta is a function of space and time. So temperature is different, but the universe is smooth. So the reason why theta is different at different points is part of initial condition. We won't go into why it comes out, okay? But it is smooth. So even in such a case, that is, when the universe is smooth, these two are zero, still there is a non-trivial evolution of theta. Okay? So this is, so if suppose there is no collision, this will be equal to zero. So suppose I have no gravitational perturbation, even then, so if I have psi equal to 0, phi equal to 0, even then I will have del theta by del t plus pi by a del theta by del xi equal to 0. I will have a non-trivial evolution, which is understandable. Why is it understandable? It's very interesting. You see, look at it this way. Actually, this is a very intricate thing, and it basically has to do with the fact that if you have a monopole term a dipole term in isotropy which is created, as you proceed in time, you will start producing higher order terms. And it happens because of the following reason. Let us go back to my favorite 1 plus 2 dimensional example. Okay? So I have this one, and suppose at a particular time, the theta is not uniform, but there is higher theta here, lower theta here, and so on. And suppose the observer is here, and there is a patch which is high theta. So what happens? This person will see it in this background light cone, and the person will see that all directions are same. So it's a monopole component. It is L equal to 0. It's the same in one direction. However, this value is not same as the homogeneous value. Because it is like this. Suppose I am sitting inside, okay, so suppose there is a fish inside water, okay, and it can see, say, just 1 meter. Then you see that the universe is all uniformly with some density, okay. However, if it sees a bigger distance, it will see, here it is water and there is air. So in other words, if one is seeing larger and larger portion, you will start perceiving the anisotropy move. Okay? So it means that what can I go? Let me just rub this off. So for example, suppose this is where the fluctuation is, and the observer is sitting here, and the observer is seeing along a backward light cone, and the observer is seeing this. Now suppose, so suppose for example, the temperature has a high temperature on this side and a low temperature on this side. So as the observer scans it, the person will see a dipole component. It is maximum here, it keeps reducing, goes to minimum, increasing, it's a maximum. This is a dipole component, L equal to 1. You understand? You see, if you have a function, okay, as a function of theta, and this function is a constant, and you do a spherical harmonic analysis, it will contribute only to L equal to 0, which is a monopole term, which is a constant. If it has a constant plus a cos theta factor or a sin theta factor, then it will be a L equal to 1 term, and there it will maximum one direction, go to minimum, come back to maximum, because that trigonometric function has a periodicity of 2 pi. Okay. So the person sees a periodicity of 2 pi. The maximum here keeps reducing minimum and comes back. So this is a dipole. What the person does not see is that it is maximum, minimum, maximum, minimum, similarly minimum, maximum, minimum, maximum. The person only sees this portion, so one thinks it's a dipole. If at a future time, the person looks at this circle, the person will see more number of ups and downs in the temperature. So in other words, higher values of L are being generated. Okay? So this is exactly what is happening here. So this is the kind of evolution of theta with respect to t. So if you have a given temperature distribution, even though there is a uniform background, just because of the fact that you are seeing bigger and bigger circle of loss scatter at a future time, there will be more amount of anisotropy which will develop. And that is why even when the perturbation is 0, there is the time evolution of anisotropy of the microwave of the temperature. I know see, these are things in which you will completely understand it only when you dirty your hands by calculating. But do you understand the basic philosophy of what I am saying? No. You see, when I was a child, I used to go to my grandparents' house in Bombay. There used to be a beggar who used to come on every Saturday. And he used to beg, saying, please give, please give. Finally, he will say, dene wala ka bhi bala, na dene wala ka bhi bala. So, if you say you don't understand, then I am happy that then I can explain to you again. If you say you understand, then also I am happy, that you have understood. Okay. So, fine. So, this is to do with the evolution. Now, at the same time, suppose we take the other case. When there was, initially theta was uniform. Theta was 0. Even then you will find that because of this perturbation, it will develop theta. So, which is again understandable. Because, you start with a plain rubber sheet, okay? But because of some processes, the rubber sheet can shrink in between. So, initially it is all uniform, but later it has got formed because of the gravitational perturbation. So, this can be neatly put in two additive terms. This is called the free streaming. Free streaming means it is just because I am moving in time and seeing more and more of it. Okay, that is, the photon is just free streaming towards me. And that is why I am seeing more and more of the anisotropy. That is these two terms. And this is the one which can cause the anisotropy even if it does not, even if it starts with an isotropic situation. Okay? Fine. So this is the situation as far as pure gravity is concerned. Now we bring in the collision term. Okay? So, if suppose the universe had no baryons, of course, no baryon, you and me will not be there, we won't have this lecture. But suppose we were all test baryons in the universe, and the universe consisted of primarily dark matter particles and radiation, then this will be the end of the story. Okay? Most of the complication arises because of baryons, because it undergoes electromagnetic interaction. Okay? So now, if suppose there are collisions, then what happens? If there are collisions, instead of this left hand side being 0, this has a collision. So just because we have called it C of F, we will be very happy that we have understood it. Okay? So let's go to the details. So the collision, the primary collision process which affects photons is the collisions between, when I say again collision, I mean electromagnetic interaction between photons and electrons, free electrons before recombination or whenever. Okay? So the collision term is actually E, which is a function of what is the notation Q plus gamma P going as E minus Q prime plus gamma P prime. Okay? And the collision term, now what you have to do is, sorry, see, you have to put in the distribution function of these electrons and the photons and work it out. By the way, I should mention this. The portion which I am doing this one, although it's not ditto in the same sequence, but it is primarily from modern cosmology by Jordanson. Okay? There are a few things which Jordanson has mentioned which I think is wrong. He's really trying to cheat you. Okay? What he has basically done is, in some equation, he has neglected some term. He says we will soon justify it. He first neglects it, solves it, and from the solution he said this can be neglected and hence self-consistent. So yesterday, for the heck of it, I tried out not neglecting it and neglecting the other side. Then also it is self-consistent. Okay? Okay? So other than these few things, but the only problem with that book, which I find personally, is that the person will tend to give all the results first. Okay? And then he will go to the details. And often one is confused, as to what is what came first and what is afterwards. You know. So if you are just careful about these things, I mean, Doddleson is a very good book for it. I mean, it's just that you need to read through the chapters, understand them in pieces, and put them back in a different order the way you understand it, then it will be okay. So now, the details of this are given in Doddleson's book. So the C of F comes out to be summation of Q prime, Q, P prime into what we call amplitude square into F of the electron, this one, F of the photon as a function of P minus F prime of the electron, F prime of the photon. That is, this is, I mean, a before and after collision. Now this amplitude here, I mean, clearly if there is no collision, okay, if there is no interaction between photon and the baryon, then this will be, then this has to be 0, and that's achieved with this is 0. So this basically amplitude is depends on the interaction cross section of the process. Okay, and here there are a few comments to be made, which is that technically for electron you will have to use a Pauli factor, which is an addition, another multiplicative term, which will be 1 minus F. That is, if there is already an electron, there will be more difficult. The another electron cannot sit in the same space because of Pauli exclusion, which means that there will be a slight Pauli suppression, and there will be a Bose enhancement for a photon. That once there is a photon, there is an additional probability of a photon coming in because Bose enhancement. But in the cosmological context, the density of electrons and the density of photons are so low that this does not play a role, so we will neglect that factor. Okay. So do you understand this point? You see, in the distribution function, you always have this Pauli suppression factor. If you already an electron, then the probability of an electron going in the same nearby phase space is lesser because of Pauli exclusion. Okay, but this does not include it. Also, the fact that there is a boson, there is an additional probability of the boson occupying it, Bose enhancement. But both these happen only when the phase space density is large. Okay, there are quantum effects which show up only when they are large. The phase space density we are talking about in